Welcome to the first lecture of this course. Before we get into any algorithms, keys, hashes, or anything technical of that matter, I want to start you guys off with a simple question. Why does cryptography matter to you? Maybe you build softwares, maybe you test it, maybe you work in QA and you're seeing words like TLS, JWT, AES, or encryption tickets and code reviews. Or you may understand it, but not enough to feel fully confident on the matter. This is why this course was made. Cryptography can feel intimidating because people often explain it like it's pure math, but for developers and QA engineers, the first step is not to memorize the algorithms, but rather it's to understand the purpose behind them. What is this tool solving? What can go wrong if it's used incorrectly? And how will you know if it's working? That is the mindset I want you to build throughout this course. So what is cryptography? At the very ground level, cryptography is a set of mathematical tools that software uses to protect information. It's a group of tools where each tool has its own job. The reason why it may feel complicated is because modern software moves data everywhere. Data travels across networks you don't control. It sits in databases, it moves through APIs, user logins, files get uploaded, payments get processed, and messages get sent. And a lot of that data is very sensitive. Password, medical records, financial details, personal messages, and identity information. We can't risk leaking that information. And cryptography is the main layer that protects the data from people who should not see it. Let's make this practical. When you log into your bank, TLS protects the connection before your account information travels across the internet. When you create a password, the application should never store that password as plain text. It should hash it, which means it turns the password into a one-way fingerprint. When you message someone in an app like Signal, encryption helps keep the message private from anyone who shouldn't see it. When a software vendor sends an update, they can sign it so your computer can check that no one has tampered with a file before it reached you. This is not very advanced, it's normal software behavior, and as a developer or QA engineer, you may not write cryptographic algorithm yourself, but you will absolutely work around systems that depend on it. Here's one important part. Cryptography doesn't protect everything. It's not just one giant shield that you add to your system and forget about. Each cryptographic tool solves a specific problem. If you don't know what problem the tool is supposed to solve, then you can't really tell if it's being used correctly. Therefore, you cannot test it properly, and therefore you cannot spot the weak point. So before we talk about specific algorithms, we need a simpler framework. Most cryptographic tools are trying to help with one or more of the four goals: confidentiality, integrity, authentication, and non-repudiation. Once you understand those four goals, the rest of cryptography becomes much easier to organize in your head. The first goal is confidentiality. Confidentiality means only the right people can read the information. If someone intercepts the data, they should see scrambled information and not the real message. This is what encryption helps with. You can see this in HTTPS, encrypted database fields, and end-to-end messaging. The second goal is integrity. Integrity means the data has not been tampered with or the data has not been changed. The file that arrived is the same file that was sent. The main idea is so that we can know whether or not the message has been modified by accident or by attacker. This is where hashes and message authentication codes come in. This is the really important part. Encryption and integrity are not the same thing. Encryption can hide the message, but that does not automatically prove that the message was not changed. The attacker may not be able to read the encrypted data, but they still might be able to tamper with it. So, confidentiality answers, can someone read it? While integrity, on the other hand, answers if someone changed it. These are two entirely different questions. Now let me show you why that difference matters. Imagine the original message says, transfer $100 to Alice. The system encrypts the message with AES, so now it looks like random noise. An attacker cannot read the original message. But if the system did not check integrity, the attacker may still be able to change parts of ciphertext. They don't need to understand the message, they only need to tamper with it. When the receiver decrypts it, and maybe the message now says transfer $900 to Mallory, but the attacker never read the original message, so confidentiality worked, but the integrity failed. That is why modern systems usually combine encryption with an authentication tag. The system should not only hide the message, but should also detect if someone has touched it. The third goal is authentication. Authentication means you know who you're talking to, not just because someone claims to be the bank, but the system can prove it. For example, when using a banking website, the TLS certificate helps your browser confirm that the server is really the one it claims to be. SSH keys work in a similar way when you connect to a server. They provide identity to prevent impersonation. The fourth goal is non-repudiation. This one comes out a lot in legal and audit and compliance situations. It means a person cannot easily deny that they performed an action. For example, if I sign a document with my private key, that signature connects that document to me. Later, I can't just simply say, I never signed that, because the signature proves that I did by providing the evidence. Authentication says, I know who you are, while non-repudiation says, you cannot easily deny what you did. Now, let's connect this to real features. On our login page, HTTPS gives you confidentiality because it protects the password while it travels across a network. It also gives authentication because the browser can confirm that the user is talking to the real server. Password hashing protects stored passwords if someone steals it from a database. They should not be able to see plain text passwords, they should be able to see hashes. JWT tokens are another example. A signed JWT helps protect integrity because the server can detect if someone changed the claims inside the token. It also helps with authentication because the signature proves that the token came from a trusted source. Signed software releases protect integrity because the user can check that the file has not been modified. They can also support non-repudiation because the signature connects the release to the signer. This is a pattern I want you to practice. Look at the feature and ask what it protects, and then map it back to one of the four goals. One more thing before we move on. Cryptography is strong, but it's not magic. Algorithms like AES, RSA, and SHA-256 are very strong when people use them correctly, but in most real systems, the math is not the part that breaks first. It's usually the implementation. A developer chooses the wrong AES mode, someone refuses an IV that should have been unique or random, a password gets stored in plain text because the hashing step was skipped, a certificate check gets disabled during a testing and never gets turned back on, a JWT library accepts non-algorithm, which means that there's no real signature check. These are all examples of failures that don't stem from cryptographic math. Those are failures in how the software actually uses the cryptography. And it's exactly why developers in QA need to understand this topic, especially in the common day of age where cybersecurity attacks are becoming more common than ever. There is a huge difference between saying the algorithm is secure and the system is secure. This is where your role matters. A system can use a strong algorithm and still be unsafe if the implementation isn't up to par. That is what this course is really about. It's not just about naming cryptographic tools, but rather understanding what they protect, how they fail, how to test them, and what evidence prove they work. From this point forward, every section will come back to one of the four questions. What does this protect? How can it fail? how would I test it, and what evidence would prove it works. In the next lecture, we will cover just enough math to make the rest of the course easier. Not too much, but just what you need. Let's keep on moving.